Hi class. So this is an introduction to friction. Make sure you watch this video before doing the learning catalytics modules because you're going to need information from this video. Okay, so we have been talking about friction, but we did not define it officially. Now here's the definition. Is a force. Of course, we're looking at forces, so it is only fitting that friction is a force that opposes relative motion between surfaces in contact, okay? And it has two main characteristics, two main things that you can relate to friction, and they're part of the friction. And the first one is parallel, so along the same direction. No, not the same direction, sorry, it's parallel. So parallel. Oh, what's wrong with my handwriting? Let's try this again, guys. I don't know what's happening. My OneNote is being weird. Do you see that? And against the motion. Parallel and against the motion. Basically what it means is if something's moving to the right, then friction is going to be to the left. Okay? That's it. And now we used to have force of friction, and we'd write it as F sub F. But now because we have too many forces, we have a lot of F to describe forces. We're going to use the lowercase f. That's friction. And it has an equation which is called, this is coefficient of friction times the normal force. Don't forget it's that funny looking n. So this, what it means, or the way we can read it, is friction is equal, come on OneNote, to the coefficient of friction, come on, times the normal force. That's what it means. Now, normally we have kinetic and static friction, and we're going to define what those are, or kind of just explain what those are. So kinetic friction, well, let's start with static. Static friction. My handwriting's even worse without my Promethean board. We write as F sub S because it's static, friction static, and that is equal to the coefficient of static friction, mu sub S, times the normal. This letter, I didn't say it right, this letter is the Greek letter mu. So let me show how it should look. It should look like this one. Where did it go? I don't know. So let me have it. it should look like this one. You know, it's not that different, right? So that's the, excuse me, the Greek letter I'm going after, mu. Okay, just so you know, that's the coefficient of friction. And normally when we have static friction is when objects are stationary. Normally we have an inclined plane and we have a block or a box that is either sliding down or just resting on the inclined plane. If it's stationary, then it's static friction. So stationary, or you can write no motion. And then we have kinetic friction, right? This is coefficient of static friction, and this is, and then we have kinetic friction. And the word kinetic comes from the Greek kinesis. Think about kinesiology, kinematics, kinesthetics. It has to do with motion. Oh, come on. I'm telling you guys, this thing does not like me. I think I'm going to charge it, this pen. So it would be friction kinetic is equal to coefficient of friction kinetic times the normal. In this one you have relative motion, that when the box or the block is sliding down the inclined plane, I think you're gonna have a problem with someone skiing and going down the hill. So there's relative motion, there's motion, so you have kinetic. Okay. The main things: friction is a force, it's against motion, and it's parallel to the motion, meaning it's along the same axis, not along the same direction, right? It's the opposite direction, but the same axis. So normally it's about the x-axis, right? Because normally things move on the x-axis when we have them like on an inclined plane or on a table, and then friction is along the x-axis but in the opposite direction. Okay, make sure you write. We're going to use these formulas. This is normal force, don't forget. Okay, now how can we use friction? Well, here's an example. Let me make this smaller so you can see it. There you go. It says write a mathematical model for the following situation. Now this looks very complicated, guys, but it's not complicated. That just means we'll draw the free body diagram, find the forces, and then sum the forces, okay? It says write a mathematical model to describe the following situation. A block of mass m rests due to friction on an inclined plane. So the first thing we do is draw the free body diagram. And if you're not sure what the forces are, there's one force that is always present here on planet Earth, that is the weight, right? The force of gravity, the weight of the object. Now some students make the mistake of saying, oh yeah, like that, because it goes down. However, think about what would happen if the inclined plane was not there. If it disappeared for some reason, right? The box would not fall like this, or the block wouldn't fall in this direction. It would fall straight down, just like that, straight down. And this is the weight of the block, which we'll call mg. We know m, well, m is a variable, right? So this is mg. Now, I know the block is at rest, it's not moving, but let's say if this was a frictionless incline plane, this block would move along the incline like that, right? So that means friction would be parallel, so along this axis or this direction, well, this axis, but in the opposite direction. So then friction is against, like that. more or less. There you go. Now we're missing one force. We said that anytime we have an object resting on a table or on the floor, there is a normal force which is against the weight of the object, right? We call that the normal force. The reason why it's normal is because it makes a 90-degree angle with the surface, in this case the inclined plane. That comes from mathematics. A normal vector means 90 degrees. So then 90 degrees, and I'm just going to exaggerate so you can see 90 degrees, right? Let's get this centered. So there's 90 degrees with the inclined plane. And there you go. Now let me just make sure this is correct. You'll see why I'm saying this. There you go. You'll see. I think you saw what I'm about to do, right? So these are the forces that you would have to draw for the free body diagram. We know this is the normal force, weird and this is friction. Now it's not moving, so it's friction kinetic. I'm sorry, static. Static, not moving. There you go. So now we know that the force acting against friction has to be along the same axis. And one cool thing about physics, guys, is you can change your coordinate plane to make your mathematics easier, and that's what I did. I rotated my coordinate plane a little bit so that this direction along the inclined plane is the x direction. So we don't have this like traditional y and then x, but now it's a little tilted. So it matches our motion, okay? So that means there's a force equal and opposite to force of friction. I'm going to use green just to illustrate that force because it's a component of another force. So it's equal and opposite. It has to be parallel. There you go. Like that. And think about it. Why would it slide down the incline? What is making it slide down? Well, it is the weight. It is gravity, the force of gravity. So then this is the component of gravity along the x direction, because this is the x direction. That's why we rotated our coordinate plane. Okay? And then, well, before I continue, some books call it mg parallel because it's parallel to the surface inclined plane. You can do that, but I'm just going to say along the x direction because that is what we have been doing. And now, the normal force is acting against a force equal and opposite to it, right? Not just the weight, because the weight is not in the same axis, right? But there should be a force equal and opposite to the normal force. So then it would be like that, equal and opposite. Here you go. Now what we'd have to do is our task would be to find these two forces, to describe them in terms that we know. And when we talked about vector, we said the cool thing about vectors, you can move them. So if I move this over here, look what I have. Your favorite, a right triangle. So I'm going to copy this to show you what is it that we need to do when we have our triangle. Okay? And then I'm going to delete these blue ones, and I'm going to move this vector back where it was. But it's the same, right? It matches. Or I could even move this one down here. It'll be the same. So I'm sure you can see the 90 degrees here. And then this is theta. It corresponds to theta, right? Because of geometry, we know how angles work. So let's do that theta again. This is ugly. One more time. There you go. And we said this was the mg component along the x, and this is mg component along the y. Again, the reason why this is x and y is I rotated our coordinate plane just a little bit, okay? There you go. Now, we need to find mgx and mgy. I'm sure you know how we're going to do that. We have right triangle, theta, so SOHCAHTOA, trigonometry. And although we have been using sine for the y, anything with the y direction, now it's going to change a little bit because theta is in a different place, or a triangle looks a little bit different, okay? So let us start with the sine. So the sine of theta is equal to the opposite divided by hypotenuse. The opposite of theta would be mgx. mg along the x divided by mg, because this is hypotenuse of the triangle. So I'm trying to find, let's solve for mgx. Let's isolate mgx. So I multiply times mg here and here. These two cancel. And now I have that mgx is mg sine theta. For cosine, it's going to be almost identical because we have cosine of theta, but now we have adjacent divided by hypotenuse. The adjacent is mgy. Don't forget, adjacent is just a fancy way to say next to. So mgy divided by hypotenuse, which is mg. We solve for mgy. So then mgy is equal to mg cosine, cosine, come on, theta. I'm going to move this a little bit. These two equations, guys, are very important. You're going to use them many, many times. This is why they're boxed. There you go. So now we can add those forces, those components here, right? This is mg, the one of the x was sine theta. And this is mg cosine theta. Okay, now let's do the mathematical model. So let's sum the forces. We're only going to use forces along the x, along the y. As per our coordinate plane, forces along the y, forces along the x. Let's start with the x. You can start with the y, but I want to start with the x. So in the summation of forces, this is sigma, forces along the x would be, we said that we're going to make the direction of motion positive. In this case, I know it's not moving, but let's say if it was a frictionless, or the friction was very small, then it would slide down in this direction along mg sine theta. So we're going to make that one positive because that's the direction of motion if it were to be moving. So mg sine theta minus static friction. This is not moving, so this will be equal to 0. And of course, if we move force of static friction to the right by adding, then we can prove these two are in equilibrium because they're equal and opposite to each other. Okay, that's why it's not moving. So now let's do the summation of forces along the y. And let's make up positive, right? Well, we kind of have to because this is positive y, this would be negative y. So then it would be the normal minus mg cosine theta is equal to 0 because they are equal and opposite to each other. Okay, that is it for now.